Okay, so today I'm trying a new setup. I am using Zoom, and then Tobias is gonna join here. And so the idea is that if there are people that want to participate, then they can contact me and we can set up things. That's basically how it would work if everything works decently today. And now I can try sharing things through Zoom, which is this. Okay. And is the resolution. So what I cannot do that I was able to do in the other setup was to make sure that things were pixel perfect. Here with Zoom, I have very little control. I can't even see exactly what's going on. So I don't know whether the quality is good. Oh, it seems to be readable. The part on the left is not that good. If I make this smaller, is this better or not? I've also set up, in principle, the streaming so that there is less delay, so that the chat should be a little bit more usable than usual. And we'll see. Is this better readable or not? Yeah, it's a little bit better. But again, it's not going to be pixel perfect. Okay. So where were we? Last time we had the sensible idea to go and understand the issues with infinite dimensional spaces. And so that's what I was going to go and do today, to understand, fully map what the problems are, because it comes to the realization that we're never going to be able to fully do reverse physics and quantum mechanics for infinite dimension, because if the math is not there to capture all the things that the physics needs to capture, we can't go back and forth between the physics and the math. So that's basically it. So let's plan this. So I have an introduction that basically outlines the problems, and we can review what I've written later. And then I was thinking that we need a section that basically says that all the infinities become the same thing in Hilbert spaces, and therefore we're not going to be able to distinguish between infinitesimal and infinities. Everything is bunched together, and any number of infinite dimensional spaces are the same. So let's put it like equivalence of Hilbert spaces. And then this part, I would put it here because it's one of the problems. One of the problems is that we can't even tell how many degrees of freedom we have. Okay, which is, so to do, we cannot tell how many degrees of freedoms are there in the space. And then the other thing that we cannot do, we cannot distinguish between essentially spaces with infinite ranges with between something and something, between space with infinite and finite continuous ranges. So we can distinguish spaces with infinite discrete ranges, and final continuous ranges. So these are the things that are not going to work. And then we can talk about the continuous spectra and domains of operators, and then Schwartz space, and then there's a whole thing about probability on a continuum. This is going to be something that we also started talking last time. We talked about this lighthouse problem, where distribution on a finite range becomes a distribution of an infinite range where there is no expectation value. Though there is a problem there because, oh, there's a Q&A. I see Tobias here. Tobias, let me change your setting from attendee to panelist. And we need, Tobias, we need to use the chat, or at least for today, we're going to use the chat on YouTube, because this chat will not have the replay, and people who watch from YouTube do not have access to the chat on Zoom. So the issue is really that we need to understand whether, I think the live stream needs to be on YouTube, because otherwise, like, nobody else can follow. And then some people that participate and are interested can migrate to here. But the chat, if we use the chat inside Zoom, we are not going to have a replay, and so people who are streaming do not see what's happening in the chat. Unfortunately, the interoperability between Zoom and YouTube is either not that great, or I don't know how to use it. So one of the two is true. Okay, so these are the technical things that we still need to figure out. Another thing that may or may not be useful, I just checked this morning. In principle, Overleaf has a mode to share in view mode. So in principle, instead of working on Text Studio, I could be working on Overleaf and put a link in the YouTube chat that people can click and look at things. I want to test it first, so I don't want to do it today, but if it's something useful, maybe we can even do that. So we're still trying to understand how to do this, quite frankly. I have no idea how to essentially do open-ended group meetings on the internet through YouTube. I have no idea how that works. So we are not only researching in the Foundation of Quantum Mechanics, we are also researching in how to do essentially public research or open research. I don't even know how to call it. Okay, so going back to the task at hand. Yeah, I was talking about, Tobias, the problem that you brought up last week, which was this lighthouse problem. And what I realized is that, and this is a conjecture that I have at this point, to be able to have, okay, so I should probably rephrase it for people that don't know what I'm talking about. So the idea is that you have a lighthouse that actually sends a signal over a range of pi, and then you have an infinite shoreline behind, in front of the lighthouse. So the light is going to hit some point in the shoreline, and so you're going to have a probability distribution on the shoreline. And the idea is that the expectation value, or even the square of the expectation value on the shoreline, becomes undefined, and the expectation that the variance becomes infinite, because you get this Cauchy distribution that has no variance, so an infinite variance. And what I was realizing when I was thinking about this is that to get the distribution of the shoreline, you need the infinite time. if you get at any finite time, right, then at any finite time, the light has propagated a finite amount, and you're going to have a finite distribution on the shoreline, and therefore you're going to have all the expectations that are going to be finite. It's only when you make things at infinity that you get a change from finite expectation to infinite expectation. And so this is still the same conjecture that I have in the context of quantum mechanics and inequivalent representation and all that. And the idea is that you change finite expectation to infinite expectation only if you have a process that takes an infinite amount of time. If you have a process that takes a finite amount of time, you shouldn't be able to do it. You should be able to go from finite expectation to finite expectation. And so I think that's a constraint on the dynamics. And now I don't know whether these constraints are already embedded, let's say, also in classical mechanics or not. And that's so one of the conjectures that I have, for example, is whether finite expectations map to finite expectation if and only if the velocity is bound. So clearly, if I have you start with a set of points, you map them to another set of points, and then you transfer the probability distribution. If the speed is bound, then I cannot see how you can go from finite expectations to infinite expectations. And I think it should work in reverse as well. If the map is such that the velocity is not bound, meaning that there are some points, every point is mapped to another point, so there's going to be a velocity from that point to the other point. If those maps between points, you can make them such that there is a sequence of points that can map with a speed that it's greater and greater and greater, then you should be able to put a distribution on the initial space that gets mapped to a distribution in the finite space where the expectation of velocity or square of position or the query position is infinite. And that's something that I need to check. And yeah, those things are it's probably part of trying to get more of a sense of what exactly in statistical mechanics is allowed or not. This is an interesting problem to me because when you do differential geometry, one of the things that you do is that you exclude essentially coordinates that are not differentiable. So the way that the thing works is that you start with a manifold, when in principle you can have all the coordinates that preserve continuity, that preserve the topology. And then you say, okay, but we need a differentiable manifold. We not only need continuity, we need differentiability. And so you essentially throw out all the coordinate systems that are not differentiable to one. And so the differentiable structure is essentially that, is the ability to go from one set of coordinates to the other and preserve differentiability. And so I suspect that if we want things to work with statistics, we need to map. We need to only consider those change of variables that preserves the finiteness of the expectation value. And so that might be an extra constraint that we actually need on the set of spaces to be able to make sense of things. So one of the things that you could do in a differentiable manifold, for example, is go from a coordinate x to exponential of x. And you can, in general, take something that it's an infinite range and restrict it into a finite range. And so if you're able to do things like that, of course, you're going to have all sort of problem with the statistical quantities. And so there might be a sense in which so the physicality of the space knows about this, because these things are not going to make so much sense physically. So these are things that I think at the end of the day, we need to fully get a handle, and also in classical mechanics, essentially. And then in quantum mechanics, things are just going to get worse. They're not going to get better. So if you don't understand them well in classical mechanics, we're not going to be able to do them in quantum mechanics. So basically getting necessary and sufficient conditions on, let's say, the dynamics for how this works and which coordinate transformations are good. I think it's useful also because if you have a deterministic reversible motion like like a Hamiltonian evolution, all evolutions are equivalent to a passive coordinate transformation, because the idea is that if knowing the past and the future is equivalent, then what happens is that using past or future coordinates is exactly the same. So it is. So you could use right now the future coordinates, right? And that's still a coordinate transformation that you're just relabeling things. And so you have perfect equivalence between a passive transformation and active transformation. And so whatever constraint you're going to have on the passive transformation, you're going to have on the active transformation and vice versa. So that there is some interesting interplay there that, again, I need to fully understand how it works. Right now, it's just words. Okay, so I see that Cram has joined us, and he seconds the idea of putting things on overleaf. I'll then set up things for next week like that and see how it works. And okay, so I would go through the thing that I've written like 10 minutes before joining. And so that should actually be the problem that we have for today. So I think it makes sense to try to solve the hard problem first instead of doing the things that are easy, because then we can concentrate. We know what are the boundaries of what we can do before. So let's pretend that we have a previous section, and then I write, in the previous section, we restricted ourselves to finite dimensional spaces. In these spaces, all measurements can be understood as having finitely many outcomes, and all those outcomes can be understood as quantum states. In this section, we will extend the discussion to the infinite case and see the extension is problematic. Infinite dimensional Hilbert spaces, I can even do some typos, in fact, seem to hide the source of the infinity and require the existence of states that cannot be thought as being physically meaningful. The exact mathematical representation of these cases then is still an open problem. Okay, so that's basically my paragraph, introduction paragraph that tells me what we're going to talk in this section. Okay, so Cram says, for which one remember some blog posted by, I want to say, John Carlos Baez, where even in a relativistic setting with finite top speed, things break. Oh, quantum mechanics with a lower bound on energy fixes explosive problems, though. I'm sure that it's quite relevant to this Cauchy distribution issue, but the way you describe it, they're kind of similar. Okay, so if you can recover that post and then we can see whether it's relevant or not, that would be interesting. Yeah, because relativistic is exactly what I was saying, that the relativistic testing has a finite top speed, and so I would not think that their expectations of position can blow up. Though I do not know on the expectation of momentum. So I don't know if those can blow up. I would still, well, expectation of momentum blowing up would also mean, again, that the energy blows up. So it can't blow up if we have a Hamiltonian system. I would think. But again, it needs to be it needs to be understood. Very good. You're live now. Okay. So yeah, that's the other thing that is actually a lot more useful in YouTube. That if somebody arrives late, they can catch up, and if they join the Zoom, you're forever behind. You see, there is no perfect system. Like this thing is going to be problematic to understand. Okay, so so this is essentially the problem. And then what I want to characterize is that there are two potential sources of infinity. I always screw up the S's, but I don't think right now it makes sense to really, you know, because the text is probably going to be changed 30 times before we get a final thing. So there are two potential sources of infinity, the infinitely large and the infinitely small. The infinitely large comes from unbounded quantities. For example, the number of particles in a gas or the distance of a particle from the origin of a reference system can be, in principle, arbitrarily large. In this case, infinity is just the range of possible values and not a value itself. It would not make sense then to say that a gas has infinitely many particles or that a particle is infinitely distant, unless we're talking about the limit of a process that takes an infinite amount of time. And this is what I was saying before. Okay, so confirmation also on the latency that is working. The thing that doesn't work so well is that when I was streaming through OBS, I had a little pop-up for the chat that I could put wherever I wanted. And I don't have that anymore. I have to use the chat from YouTube, which is on the other screen. So I don't see the chat as readily as when I'm looking to other things. Again, it's gonna be I need to understand how to set this up. Okay, so yeah, so there should be something like that. If we have clearly the points cannot be mapped to infinity in a finite amount of time. So there has to be something there. Okay, so note that the infinitely large does not change the nature of the quantities. The number of particles is a discrete quantity, and the position is a continuous quantity regardless of whether we're lying an infinite range of not. And this is the nature of the infinitely large. The infinitely small comes from the ability to refine measurement indefinitely. For example, we can assume we can measure the position of a particle with arbitrary precision. In practice, infinite precision is never realizable, but it essentially identifies the value at all level of precision. That is, if we knew the position with infinite precision, we would know. Mamma mia, I'm awful when I write, I have to say. And if I have to do this, I probably have to reread it at least once. Maybe I should just read it from here. In practice, infinite precision is never realizable, but it essentially identifies the value at a level of precision. That is, if we knew the position with infinite precision, we would know all possible finite precision intervals. We would know all the possible finite iteration intervals in which the particle can be. The infinitely small then changes the nature of the quantities, going from discrete to continuous. Over a finite range, a discrete quantities will have finitely many possible values, while a discrete quantities will have infinitely many. Okay, so you found right, you can't post the link in the chat. As I was about to say, why don't you post the link to the chat? You can't, man. Can I at least copy the thing? Okay, I can more or less copy the thing from. Okay, so let's finish this, and then I'm curious to go and read that post. Okay, so then we can characterize these differences in the following way. A measurement will tell us whether a particular value is within a set of possible values. If the quantity is continuous, all measurements will always restrict the range of possible value to an infinite set. That is, any measurement of position will have an infinite, will have a finite uncertainty, which will include infinitely many possible positions. If the quantity is discrete, at some point we will have a measurement that identifies each possible case. That is, when we count exactly the number of particles which restrict, that is, we can count exactly the number of particles which restricts the measurements to only one possible case. Intuitively, the range is infinite in either cases if it cannot be always covered with finitely many measurements. That is, if we're given measurements with finite ranges, we're not going to be able to cover the infinite range with finitely many measurements. Mathematically, this maps to properties of concepts of the topology. The topology, in fact, keeps track of the closeness, and measurement resolution is about closeness. The topology of a real line then is different from the topology of a set of points. The first is topologically connected, while the second is not. A space with finite range is topologically compact, while one that has finite range is not. Establishing a perfect mapping between these concepts is not the goal of reverse physics, but rather of physical mathematics. The point is, in classical mechanics, the mathematics characterizes and keeps track of the differences. The problem is that in quantum mechanics, the mathematical framework does not keep track of these differences. This is the problem we're going to explore in this section, a problem that is ultimately not solved. And given the mathematical framework does not capture all the elements and only the elements that are physically meaningful, the reverse physics problems cannot be, let's say, fully completed for quantum mechanics. Okay, does that make sense? I think it makes sense to me. So, okay, so let's go and look at that post that Cram is suggesting. And let's see what it says. I find it as a paper more than a post. Let's see. The gravothermal catastrophe in gravitational collapse and energy potential of gamma ray bursts. Okay, so this might be a little bit long for me to look at right now. Yeah, this is far too long for me to look at right now.
Gabriele, can you read the Zoom chat?
I can read the Zoom chat.
Because there I can post links.
Oh, there you go. Thank you.
Yeah. That's not the paper, that's just
the
that's
blog
much
post.
shorter.
Yeah. So that's okay. So when you talk, the thing changes on top. Okay, very good. The gravothermal catastrophe. Okay, this should be, let's see, can I share that now? Let's see if I stop sharing this and then I reshare this. There we go. Now I'm sharing the everything, right? Okay, I still see a latency that is kind of unbearable when I go from the stream, but maybe it's worse. Okay, so Antonov did some remarkable simulations that in Newtonian mechanics, a gravitational system can violate the usual rules of thermodynamics. Instead of reaching equilibrium, they can get hotter and hotter. Suppose you put a lot of stars in a large sphere, and suppose unrealistically that they bounce elastically off the wall of this sphere. In fact, suppose they're point masses, so they never collide and interact only gravitationally. Also, suppose they're gravitationally bound. This means the total energy gravitational potential is negative. This means they couldn't all shoot off to infinity, even if the sphere wasn't holding them in. What happens? If the sphere is small enough, the stars will seem to come into equilibrium like a gas of roughly constant density. Antonov showed numerically that this happens. But the exciting thing is what happens if the space is larger than this. In this case, some stars will collect near the center and form a dense cluster. Eventually, this cluster will start collapse and get very hot. That is, stars in the cluster start to move very fast. Some shoot out of the cluster at high speeds. Yes, but others. So I am aware of this. I didn't know that it had this name. In fact, I think you can even. There should be. You should. What was the thing that you did? Like you can have initial conditions even in Hamiltonian mechanics where you have like just an n-body problem, and you can make things. Which is probably the same thing that they're doing. You have point particles and seeing how they work only with gravitation. And here's the thing: gravitation. You have the 1/r², and this is one of the issues that if you have the 1/r² potential, technically at that point you're not Hamiltonian, right? The system is not Hamiltonian at that point. And so in the region around that point, you should expect weird things to happen. And so if you're able to have trajectory that go like very, very close or infinitely close to each other, you are going to collect this infinite energy and make things shoot out. So that's kind of the thing that probably are describing here. As a result, all stars in the sphere keep moving faster and faster. The pressure in the sphere keeps increasing. There is this ground thermal catastrophe. I hope you see why this doesn't violate conservation of energy. The increased negative potential energy of the shrinking cluster balances the increased kinetic energy of the star, whizzing around faster and faster. It's the arbitrarily large negative potential energy of this system, which is exactly what we're saying, that makes it break the usual rules of thermodynamics. It can keep converting potential energy to kinetic energy endlessly. A much simpler example would be a bunch of balls rolling down an endless ramp. Exactly. To prevent the sphere from exploding due to the ever-rising pressure inside, you may decide to make it larger. This will help, but not for long. The pressure will drop at first, but the central cluster will keep getting hotter and hotter and heat it up all the stars around it. Eventually, the pressure will rise again. What do? There's only one way to stop this runaway temperature increase. The only solution is to shrink the sphere, fighting against the tremendous pressure exerted by the gas of stars within. Once the sphere is small enough, about the size of a dense cluster of star near the middle, you'll be back to equilibrium, or so it seems, but the temperature and pressure now is much higher than when you started. Furthermore, even when the gas of stars seem to be in equilibrium, it's not, it's just a meta step. Okay, this is another issue also, that you do not get equilibrium with just Hamiltonian mechanics. That's never, ever gonna work. If you want an equilibrium where you're increasing the entropy and you have thermodynamics, you need a process that increases the entropy. You're not going to get it for free from Hamiltonian mechanics, because Hamiltonian mechanics conserve entropy. So okay, and then there's book that part in section 2 where they vividly tell the tale of how you struggle to deal with a sphere full of stars, its temperature. Note that. Okay, so this is still a Hamiltonian system at the end of the day. I don't have a problem of Hamiltonian system exhibiting this type of peculiarities. Also, one always has to remember that Hamiltonian system can be chaotic as well. So it's not that you have to expect that again, Hamiltonian mechanics is going to be all nice and so on. No, there are going to be cases that are completely off the wall. And especially if you allow for an arbitrary small potential energy, as he is saying, like the gravitational potential, the 1/r², it goes to minus infinity. So if you put a cutoff there, right? If you say, okay, well, things are never going to be able to get infinitely close because they will have a size, and therefore at some point you have a cutoff. You don't go to minus infinity, but then you start trailing off. Like if you go inside a star, you can't. Oh, well, first you can't really go inside a star, that they would merge and become something else. So if you put those cutoffs, probably a lot of these problematic things might even go away. But the point is that I only care about, so if it is true that, for example, if we can show that Hamiltonian mechanics preserves the finiteness of distributions of positional momentum, right? if that becomes true, it's going to be true in this case as well. And that's it. So the question is, can I have a Hamiltonian system of 1, 2, probably if you can do it, you can already do it in 2. Can I have a Hamiltonian system where I set an initial distribution in position and momentum, I let it go, and after a finite time, I get an infinite expectation value of something. And my hunch is no. Why? Because I can look at the Poisson bracket between any polynomial of position of momentum and the Hamiltonian. And that's going to tell me how that polynomial is changing in time. Right? And so now, if right, I can even do the polynomial. Yes, I should be able to do Poisson brackets of polynomial times rho. That's the expectation. And that's going to be the integral of the rho times everything is okay. So Poisson bracket between the integral of a polynomial of position of momentums times rho, my distribution, with the Hamiltonian. That's going to tell me the change in the expectation value. And then from there, I should be able to know whether I can have something that blows up to infinity. Okay, so Cram says, I believe the answer to your question is yes, meaning that you can make things blow up, or that I cannot make things blow up? You think you can make things blow up? Interesting. Now the question is that can you make things blow up with again a Hamiltonian that has a minimum? I'm still looking for various vlogs on post on that. It's been so long I don't really remember the detail. Okay, the chat is a lot more useful now, I have to say. Right. If there is no minimum, the issue is that if you have no minimum, you have a point, as I was saying before, in which the Hamiltonian is not well defined. And at that point, like it would be interesting to understand exactly what is the problem. Or can you, well, okay, if you have no minimum, so, okay, let's put it like this. In principle, you could have no minimum, but going to infinity. But if you have no minimum going to infinity, I would assume everything escapes to infinity. Right? And that would interesting. You see, at the end of the day, all these problems are about infinities. We need to have a handle on the infinity, otherwise, and infinity is again can I say, an idealization. We don't have infinity. So even you say, oh yes, for this particular value of position of momentum, the energy is minus infinite or plus infinite. It just doesn't make sense. It can't be. And so it's an approximation. You say, okay, well, it goes down and down, then I don't care because I'm never gonna go close to that point anyway. And then of course you find a mathematical case where you go close to that point, But the point is that if you allowed for the infinity, you probably already had an assumption that you wouldn't be close to that point to begin. And so, okay. Okay, good. Cram, if you want, shoot me an email with, if you're comfortable, shoot me an email to tell me, a little bit about yourself, and then next week you can join us on Zoom as well. Because I think at this point the conversation would go faster if we were talking instead of you typing and so on. Okay, so what is the conclusion of all of this? Is that we have some open problems to figure out, which I would put in probability on the continuum. To do when do things blow up at infinity. So so we have, I'll put the link to this blog, and then and I should probably comment these out because otherwise they're gonna make the whole thing a mess. And okay, then basically would can a Hamiltonian system with finite, let's see. Okay, so there are two cases. One where it's finite at every point, and then three cases. So look at the following cases. One is a Hamiltonian system with either infinite or minus infinite energy at a particular point. Two is a Hamiltonian system with a finite energy, finite Hamiltonian everywhere, but possibly infinite minus infinite energy at infinity. So I assume there, if you had one direction of efficity that it's positive and one direction of efficity that it's negative, also there you should be able to do crazy things, because you go farther on one side, you pick up some energy, and then you go on the other side, you deposit it on the other side. You can probably do crazy things as well. And then a Hamiltonian system where the energy is bound from below. And I assume this is enough. And 1,4 is a Hamiltonian system with energy bound from below and above. So I assume, so the conjecture, if 3 is sufficient to preserve expectation values. And I have no idea what is necessary. So I have no idea. If you say, I have a Hamiltonian system that always preserves all expectation values, what can I tell about the Hamiltonian? I mean, that would really be the thing that we are asking, right? So suppose we have a Hamiltonian system that preserves all expectation values. What we can say about the Hamiltonian, right? That's essentially the question. Cool. Oh, hi, Kurt. What about Fox spaces though? QFT has issue if you tensor only a finite amount of spaces. So the Fox spaces are, in principle, they're still separable. They still have a countable basis. So all the mass that we have are always it appears in any countable space. So problems that we have even in a single degree of freedom for quantum mechanics, like problems that we have there are going to be similar to the problem that we have in Fock spaces as well. The difference is that in a single degree of freedom or finitely many degrees of freedom, if we are on Rn, you can imagine using Schwartz spaces, and Schwartz spaces would have all the expectation of polynomial positional momentum finite. And even there, my hunch is that if the Hamiltonian is Schwartz, then the evolution maps Schwartz spaces to Schwartz spaces. And so you'd be good. Like one of my hunches is whether you can do something similar. Like if you set things up like that, at least quantum mechanics, quantum particle mechanics works well. The issue with Fock spaces is that I have no idea how to generalize this to that case. And one thing that we could do, that I had this when I was at a conference discussing with somebody, is if we say that one of the main reasons why we want all polynomial position of momentum to be finite is to allow for a certain class of arbitrary coordinate transformations, right? Because I have position, you've defined the position to be x to the third, then we should be able to sort of go back and forth, and all my expectations should be finite, and your expectation should be finite as well. So the idea is not really that there is a dynamic that preserves this, but it's the different coordinate system that preserves this. Then you should have something similar in a field theory, and you should be able to say things like the number of particles should be, let's say, if they are finite for me, if the expectation of a number of particles is finite for me, it should be also finite for you. And since when you do coordinate transformations in quantum field theory, the number of particles is not an invariant in some sense that I still haven't figured out. So that might tell you what are the conditions that you have to put on Fock spaces and what are the observables that you need to have finite and so on. But I have no idea. So the point is that first I want to solve it for just particle mechanics, and then we're going to see whether a solution like that can hold for field theory as well. And so struggles with the continuum. Okay, so I'll put it here as a note. Struggles with the continuum. Too long to go on. I was about to ask whether you thought they were okay. Too long for now, but in part one, he shows a configuration of just 5 particles that expose to infinity in finite time under Newtonian mechanics. Is the Hamiltonian, again, does the Newtonian have a lower bound on energy? Is it like, how does it look like? Is it still gravitation, like say 1 over r? Yeah, it's still gravitation, okay. So again, I would completely expect it. I would completely expect it. But again, it's one of those silly things because I know that the gravitational potential at some point will stop because I get to the surface of the star and whatever, and I can't go inside. I can't have two, they can't become infinitely close. So if the resolution is, yeah, that infinity is an approximation, you put a lower limit, and once you put the lower limit, everything works fine, then it's just a mathematical curiosity. It's not, in fact, is gonna make, it's gonna confuse things. In later parts, he goes into relativistic and quantum pictures as well. Okay. Okay, if I have time, I'll have a look, or you can have a look and tell us. That could also be useful. Part 2 in quantum mechanics of point particles, part 3 in classical point particles interacting with the electromagnetic field. There are 8 parts in total. Wow, okay. Okay, so this still points to the fact that we should do all the reverse physics, the first part, the important part in the finite case, and leave this the infinite case a little bit open. Like start mapping it, but we are not going to be able to solve it. It's since we can do a lot of stuff for quantum mechanics first, it definitely needs to be like that. Okay, so why don't we start writing down some of the actual problems that at least we have more a handle on. So, for example, so do I have an argument for not wanting separable spaces? I mean, the only argument that I know is based on the connection that we have in physical mathematics between open sets and verifiable statements. Does anybody know of a different argument that says why we can't not have a Hilbert space in quantum mechanics that is that has more than countably many a base that it's more than countable. I quite frankly don't have one. Like it would be nice to have more than one, I guess, and I only have that one. Okay, so but the first thing is that the equivalence of Hilbert spaces. Okay, one feature of Hilbert spaces is that the cardinality of the base fully characterizes the space. Cardinality, that's spelled correctly, right? Why don't I have it already in my, yeah, okay, let's add it. In fact, by the way, Kurt, did I answer your question? I hope so. Math cal H1 and H2 be two Hilbert spaces that have the same just basics and let's say E I, and this is I in I, and these should be I and I. These are elements of the first one. So in mouth carriage 1, and then this thing E, and we call these G because let's call them A and B. That's probably nice. A and B in H2, B two bases, two orthonormal bases of the respective spaces with the same cardinality. Then we can write a map such that let's say the map, we call it M, from this to the other one, such that M of usually I call A and B coefficients. So let's go back to the E and G. M, A, I, then E, I, and let's put a sum. Equal AI, maybe a sum of AI, GI. We can define a map M such that that thing, this map is in the map is unitary since okay, to do write the expansion of the inner product. Okay, and then let's do it like this. Begin equation, and then I'll just write a to do here, which means the two spaces are unitarily equivalent, and they're unitarily, say unitarily equivalent, and therefore as Hilbert spaces they are the same. Okay. And therefore they are the same in space, and therefore they are the same Hilbert space. Very good. Unitarily, maybe I have to spell it correctly. Unitarily. I don't know how to spell unitarily, evidently. Okay, so which means okay. Oh, there is also all the other thing about states being equivalent classes of wave functions. That's also going to be a thing. I don't know where I would put that. I would put it here. Subsection wave functions and equivalent classes. This is where I was. Do you want typos to be pointed out? Yeah, I don't think we do typos right now because when I write, there are gonna be a million of them anyway, and the text is gonna be reviewed like so many times. If we had sort of an interactive overleaf, it might be worth for, you know, while I'm typing, somebody goes and fixing the typos. But at this point, I don't really think it's so important. You know, again, if we had another interactive overleaf, somebody could, you know, expand the equation here while I work. So there could be a way to actually like type things more than one. It's just that then I have to understand the legal stuff. Like we need to have a copyright agreement and all that stuff done, which it's a pain. But anyway, for now, I'm happy just you guys checking that I'm not saying nonsense. And what I was saying about the wave functions is what's the name? Yeah, so at some point I was trying to understand what type of wave functions are valid function, right? And if something like the function that it's 1 over the rationals and 0 over the irrational is a valid wave function. Well, it turns out that it is a valid wave function because the Hilbert space on wave function picks up only the things that make the integrals different. And so if you have a sort of a 0 function and you just put 1 at 0, right, something like that, all the integrals of that functions multiplied by another wave functions do not change, whether you put that 0, the 1 value at 0 or not. And again, if you do it on a measure 0 set, like the rationals, again, it doesn't make any difference. So technically, a wave function that is 1 over the rational and 0 over the irrational is still a valid wave function, and it's equivalent to the null state, to the 0 state. Okay, so yeah, so I think that we're gonna have to talk about that as well, because it's yet another of one of those things that nobody really talks about when they introduce wave functions and so on. And so, yeah. Okay, so what is the point here is all spaces we are interested in quantum mechanics are going to be countable. If we imagine to extend the space of a discrete, the range is extend to infinity the range of a discrete observables, we can see that we will have a countable basis for a countable set of possible outcomes, and therefore a countable basis. If we take the space of wave functions in either a finite or infinite range, okay, yes, I know that. In either finite or infinite range, we will get the space of square integrable functions, which also has a countable basis. To see that, note that the harmonic oscillator, the Hamiltonian for the harmonic oscillator is has a discrete spectra and therefore has and has a count. If it's discrete spectra over a continuum, it has to be countable. Yes. Can you have a discrete spectra on a continuum? No, if you have a discrete spectra on a continuum, it's not dense, so there has to be counted there, and therefore has countably many eigenstates, which will form a basis. All wave functions then can be written as a superposition of eigenstates of the harmonic oscillator, and therefore the space has a countable basis. Okay. In quantum mechanics, then, if the space has an infinite basis, it will be a countable spaces, which leads to the following observation: all infinite dimensional spaces in quantum mechanics are equivalent. If we have an infinite dimensional space, then we are not going to be able to know whether we have a discrete quantity over an infinite range, a continuous quantity over a finite range, or a continuous quantity over an infinite range. To the mathematically, there will be no difference in the state space, unlike in classical mechanics. Okay, so we said that. So for example, the space of one particle, which is L square of math BBR to the third, is going to be equivalent to the state space, the state space of a million particles. Did I already write down some of this? Yes.
Can I ask something about this equivalence?
Mhm.
Is it only like on set? No, like topologically, can I find a continuous map between them, or can I even like preserve the inner product, or maybe equivalent as vector spaces? I don't know exactly.
They're equivalent as Hilbert spaces, which means you can have a unitary transformation between them. And the problem, so they're continuous in the topology defined by the inner product, which has nothing to do with the topology that you have on observables. And that's the problem, right? So the topology of the inner product, the topology of the Hilbert space, knows nothing about the topology of the observables that you're trying to characterize for that space. And I think that's ultimately the big problem in quantum mechanics. And if you had a Schwartz space, then the topology is not the one induced by the inner product, because you don't have all the limits that you would have in the Hilbert space. Some limits do not converge in the space. And then the topology would know, in fact, it knows exactly the topology of the observables, because the topology in Schwartz spaces is the topology of all the seminorms of all the polynomial of position and momentum. So let's say that you take x squared and you fix a value. Now you can say all the states for which the expectation value of x squared is less than that value. That forms an open ball inside the set of Schwartz functions, right? And the idea is that all open sets can be generated by this type of open balls on everything.
So I guess there is no explicit construction of this unitary operator that maps L2 of, I don't know, R6 onto L2 of R3, because it would literally map like an integral over like 6-dimensional space onto an integral of 3-dimensional space in some way.
Yeah, but you can do this. You take let's do it for 1 to 2, right? So you take the harmonic oscillator over 1 degree of freedom. Okay, you're going to have a set of Hermite functions. So those are your eigenstates. And now you do it for 2 degrees of freedom. If you 2 degrees of freedom, you're going to have sort of the tensor product, right? The tensor product of the Hermite function will be a basis for that, for the Hamiltonian, for the harmonic, for the harmonic of a for the Hamiltonian of a harmonic oscillator over 2 degrees of freedom, right? It's just all the pairs of the product of the Hermite functions. And now you have a countable set on one side, countable set on the other side. You can map one to the other, right? So you map the ground state to the ground state. You map the first to the product of the ground state on one side with the first state on the other. The second one you map to the product of the first, the first states on both sides, and so on. So you do a diagonalization on one side. I don't know if you can see my. So you do a diagonalization, right? And on the other side you proceed linearly, right? And now you mapped one side to the other.
Okay, that makes sense. So then I could actually look at what happens to an integral over 6-dimensional space and how it in some way reduces to 1 in 3-dimensional space.
Yeah.
Okay, that might be a fun exercise.
Yes, it's of course completely crazy, but you can do it. So you're saying that quantum mechanics as it stands almost cares too little about specifically this talking about. Yes, that's a very nice way to say it. The abstract states can describe observation in a completely different system. Yes, exactly the problem. For the 1 to 2, you just do the same thing you do in enumerating non-negative rational numbers. It's the same process. It's the diagonalization. It's what you do, to prove that what's it called, that real numbers are not countable, right? It's the same techniques. Yeah. So yeah. And again, that's one of those things that a lot of mathematicians know, and most physicists don't. I mean, physically, I think it's really bad. Okay, as you said, the quantum mechanics cares too little. Like it doesn't know what it's talking about. Yeah, I think that's the right way to put it. And then what is the issue in things like quantum field theory and so on? The things become even more horribly complicated because people take literally some limits. So one of the limit is that going from initial state to finite state when you're doing a sort of S matrix type thing, right? And so you have an initial initial set of particles. You evolve over infinite time. You're going to have a different set of particles, and so the idea is that when you're mapping the observables from minus infinity to infinity, you have this mismatch on the operators, right? And that's, from what I understand, is one of these cases of inequivalent representation. You're going from a state space that is describing a set of observables to a different space that is, well, to the same space that is describing a different set of observables. And so you have this mismatch. And again, the fact that it happens over an infinite time, it doesn't bother me in the same way that we said for the lighthouse problem. Like it doesn't bother me the fact that the expectation after infinite amount of time becomes can go from finite to infinite. It's absolutely fine. The point is that what we have is always, at the end of the day, it's always finite, and it's fine that we're going to take some limits to make sense of some situation because it's nice, it's convenient, but we can't have. We need to know what are the correct states and what are the limits. And it even becomes worse when you do things in the Rigg-Hilbert space because you want to talk about eigenstates of position and momentum, because then those types of limits are even a different set of limits, and they come with a different baggage in it. But yeah, so these are the things that I think prevent us to have a fully, completely physical understanding of what the mathematics of quantum mechanics is describing. And these have nothing to do with interpretations. Like these are problem really of mathematical representation of physical systems. Like if we don't have that right, good luck having a good interpretation. Like the math can't be interpreted because there is not enough information of content. So I guess we should have that as an example then, Tobias and Cram. We'll put it as an example of the different bases. It would probably make sense because I think it was illuminating for you guys hearing it, right? Okay. Let's say n particles then. Let's do it like this. It's going to be the degree of a state of n particles, 3 to the n. As we said before, the Hermite functions, the eigenstates of a harmonic oscillator provide a... Should I talk about particles degrees of freedom? Because if I do degrees of freedom, then I can say it on one. Let's do degrees of freedom. For example, the state space of a single degree of freedom, I L square of R, is going to be equivalent to the state of the state space of n degrees of freedoms. As we said before, the might function of the provide a countable basis for a single degree of freedom. We can imagine a harmonic oscillator over 2 degrees of freedoms. In that case, the product of the Hermite functions between the products of the Hermite functions of all extension across degrees of freedom provide a countable basis for the space. We can now through diagonalization, we can map one set of bases to the other. And then here we can do the, let's see, align. And then we can have like H, we start from 0 or 1? I don't know. It's aligned or aligned? Maybe aligned. Why I always forget which one is aligned and which one is aligned? No, I think it's aligned. Yes. Okay, so and maps to H0. We can put H0 of X maps to H0 of X, H0 of Y, and then we can put 3, and then I can put dots. And so this would be 1, 2, 0, 1. Well, we can put a third one, why not? 3, and this would be 0, 2. Right. Why are these H? Oh, why do, okay. Why? Because I'm silly. Okay. This will allow to allows to map any, and this idea can be generalized to map any set of n degrees of freedoms to any set of m degrees of freedom, potentially it means that we can construct a process that can encode the information of a billion particles into a single particle. Okay, so this is what I was saying with the seems very okay. So this basically we're saying that, okay. Note that the above transformation is not possible in classical mechanics. The 1 degree of freedom topologically is math BB2, while n degree of freedom are math r to the 2, math BB r to the 2n, which are not topologically equivalent. The issue is that the topology of the inner space is the one of the Hilbert space is the one induced by the inner product and not the one induced by the observables, like in the topology of Hilbert spaces in quantum mechanics is like in classical mechanics. Therefore, the space there was more chat going on. Like before space, the mathematical representation in quantum mechanics knows too little about the physical system it is supposed to describe. Okay, so we put all these, I think we put all these points. And now I should catch up to the chat. Maybe eventually to have a figure that basically shows the guy is like, yeah. So that's where, you know, having people that can contribute that type of stuff, even the part of classical mechanics, there are a lot of figures that we could have that we don't have. Proper definition of what a big freedom is, right? Right. There is the whole argument that you can use a quick GUI to emulate arbitrary many qubit errors or just more precise. Yeah, so this is kind of like the dimensionality of the space. Like in classical mechanics, the dimensionality of the space is the number of degrees of freedom. In quantum mechanics, the dimensionality of the space is not the number of degrees of freedom. Like there is, in fact, you don't know, if you just give you the space, you don't know the number of degrees of freedom. And it's even worse than that, right? Because even when you do field theories, the space is going to be separable. And even in that case, you have a countable basis. And so it's like, even when you have infinitely many degrees of freedom, like it's still the same case. So you could map, like technically, the state of all the fields in the universe in a single particle, because it's the same state space, which of course does not make any sense. So let me. So you can use a single qubit to emulate arbitrarily many qubits. That's a qubit is for finite space. So in principle, you know if you have one qubit or a trit, a q trit, or if you know that the dimensionality of the finite case, you can tell. So you cannot, and this is where that's where even things don't make sense. So you cannot map two qubits in one qubit. That you can't do. But you can map 2 degrees of freedom in 1 degree of freedom. That you can do. So what you can do that you might getting confused with is the difference between logical bits, logical qubits, and physical qubits. That when you do error correction, you can group multiple qubits in one qubit, so that you have one qubit that is more precise, so that you have less that where you can get error correction. Like you have fewer error on the logical qubit than on the physical qubits. And it's one of the main theorems that people basically say that it allows to do quantum computers, because you're going to be able to reduce the noise. So you could be getting confused to that through that, or I don't know what else it could be. Okay, so wow, it's already 12:30. I'm wondering whether we should just stop here, because it was a good stopping point. I don't think I want to say much else, right? Because we said everything that we wanted to say here. We said that the cardinality of the base is enough. Therefore, everything is the same, and we're not going to be able to tell these things because they're all the same cases. And then we gave an example, and talked a little bit about the topology. So what could be interesting to do then maybe, but probably the planning for how to put the rest, we should, there's somebody else there. The plan to what to do next, they would probably need once we write the rest. And so this is one problem. Then there is the problem of continuous spectra, the fact that these things are not proper eigenstate. And I would probably put the domain problem next, because it connects very, very tightly to the other. Because what's gonna happen once we do those maps, and this is something that it would be nice to prove. It would be nice to prove to me that these things are exactly the type of things that map finite things to infinite things. That there is no way that that this thing is gonna map all the linear combination, right? So I would think, right, all these Hermite functions are gonna have a finite expectation for all the polynomials. And what I assume is that if I have finite expectation over, if I have a linear combination of these, right, I may get, depending on the linear combination, I may get finite or infinite expectation. And the reason of whether you get finite or infinite expectation is when you're making, when you're taking the coefficient that you sum these, right? If these coefficients converge faster than any polynomial, you're going to be fine. Like the expectation should be finite. But if the convergence is not like that, then things are going to break. And so what I suspect that happens when you're making maps like these is that you are gonna break some of these rules. And that would be nice. You know what? I'll put it here as a to-do. To-do conjecture. These maps will not map finite expectations on one space to finite expectations on the other. Which should be exactly equivalent to say that they don't preserve the topology, actually, now that I think about it. Like they do not preserve, that is, they do not preserve the topology of a Schwartz space. Right, it's the same thing. Like preserving the limits in the topology would mean that the finite expectations are preserved. So that would be an interesting question. And it's a little bit too much on my math skills to be able to prove it one way or another. Okay, but that should then become the problem of domains of operator. This is the same as saying that the domain of the operators for position and momentum on one side do not correspond to the domain of position and momentum on the other side. So equivalently, the domain of the position momentum polynomials of the two spaces are not the same. I might have a mathematician to ask that specific question and see if he responds.
Is that the same as saying that the Schwartz spaces are not isomorphic for?
Yeah.
Yeah.
So it should come from that, right? It should basically saying, look, you're not going to be able to find a map between these two things that is isomorphic. And therefore, all these things are going to be the same. If they're not isomorphic as a topological space, then the domains of the operator does not match, blah, blah, blah. So it should be all the same. So if one of these statements is easier to prove, you prove that, and then you prove that all the other statements are equivalent.
So when people actually use these Schwartz spaces, there is this kind of construction where you put like a bigger and a smaller space around your Hilbert space. I don't remember the details, but when they do this, they make some implicit assumption about which Schwartz space they actually use in this construction, right? If they're not all isomorphic, then there are different ones. And then they use the one in R3 or something, or R6.
In what case? When they're trying to do what?
I don't know exactly when people use this, but some people use Schwartz spaces.
Mm-hmm.
And if you are only given a Hilbert space, you cannot choose uniquely
Correct.
what Schwartz space it is if they're not all isomorphic.
Correct.
So when they do this, they make some implicit assumption about which Schwartz space they are using.
Yeah.
And
or which Hamiltonian they're looking at. So they take
Okay.
a particular Hamiltonian, then they say, okay, I look for a good space for that Hamiltonian, and stuff like that. Okay, so it was not quantum error correction cram, was something else. Like, if you remember, bring it up. As I was saying, I think I don't want to start anything else, and I think we have the good segue from this to go and talk about domains of operators. And so I would stop this here, and if people want to discuss anything random, I'm here. Otherwise, we can stop for today. Yes, it was fun. And I think this is starting to be what what is good. Like we have this discussion, we look at this problem, we narrow them down. So yeah, like if these live stream grow like this, I'm very happy, and it's above my expectations. So
Okay, one thing about the initial comment you made on the lighthouse problem
yeah,
about it taking infinite time.
yeah,
So, in some sense, you want this this connects to your topology argument, right? Like verifiable statements need to be, you need a test that succeeds in finite time, right? So
yeah.
ideally you should make some kind of topological statement, like you demand some kind of continuity, and that will tell you that, I don't know, this distribution on the shoreline is not physical, right? In some way.
You are absolutely. I didn't think about that, but yes, because what happens there? Ha! This is interesting. So we we are assuming that two statements that are equivalent, and one of them is verifiable, right? Makes the other one verifiable because you can use the test. But of course, if we have two tests, two statements that are separated by an infinite amount of time, that sort of breaks that assumption in some way. I'll have to think about it. But yeah, you're right. There is the issue of finite time verifiability, and therefore the evolution when I'm Okay, so here's the thing: is when I do the two spaces and I put the topologies on the two spaces, the connection between them is of the topology is only if finite amount of time has passed between them. Yes. Okay. Yes. That you're absolutely right. I don't know why I didn't see the connection, but yes.
But the map from the angle onto the position on the shoreline,
Yeah.
that is itself, I think, continuous, at least on the open set from like 0 to pi
Yeah.
for the angle. But so and it will actually take finite time. If my statement is the angle is in between this small interval, and then I map it onto the shoreline, then it is in this finite range, which is again open.
Yeah.
Then it will take me actually a finite amount of time to walk to that position on the shoreline and measure if the light is hitting there or not
Yes.
for each of those.
But
The
not
problem
to
is
make the
I
not to
can,
make the expectation, right? The
yes,
expectation. Yeah.
the expectation, like measuring the expectation value will take infinite time on the shoreline, while it will take finite time, or well, actually, you only converge is somehow to the expectation value, right? You will never
Yeah.
get exactly that, but at least if you measure directly on the lighthouse, you will in some way converge fast enough to figure out what the expectation value is, or
Mhm.
to figure out that it's kind of, I don't know, uniform,
Yeah.
the angle is uniform. While if I want to measure that on the shoreline, it
Yeah.
will take me in some way infinitely long
Yeah.
to actually find out something about the distribution, I guess.
Yeah. This you're pointing out something very interesting that I didn't think about. The expectation of each outcome, right? So the value of each outcome can be measured in a finite time, but the expectation requires the infinite time.
Yes.
Huh. That's very cool and tricky, and then that tells you why I guess the topology on the space of distributions is different than the topology on of every single outcome. Ha!
Yes. I think that's it.
Ah, beautiful. Ah, man, it's so nice when all these things come out in the right exact way that they should. This is great. This is really great. Good, Tobias. That's very good. That's very good. Any other fantastic insight like that?
No, I think that's all I can provide today.
That's good. I think you did enough. Okay, so we close it here. Cram, we close it here. Okay, we close it here then. Bye. See you next week, guys. This was very useful. Bye. And I have to figure out end stream. There you go.